Hey physicists, we'll take a look at the wave worksheet now. Okay, hey, so the first thing we want to do is identify one wavelength. One wavelength is the time it takes for the wave to make a complete cycle, so we can think of that from crest to crest. That would be one wavelength, and the Greek letter lambda is used to indicate that. But just as easily, we could end up saying that it's from trough to trough, or, it would be really fancy, we could end up saying from the center point going upward, past the center point again, to the center point going upward again. All those would indicate one wavelength. Okay, how about what? Half a wavelength. Half a wavelength. Okay, we could end up saying that's from the crest to the trough. That would be half a wavelength. Okay. Or we could look at it as being just a single bump. You notice that, hey, a bump up and a bump down make a complete wavelength. So from that position to that position is also 1/2 of a wavelength. The amplitude is the maximum distance from our center point or our equilibrium point. So in this case, hey, from the center, that would be an example of our amplitude. Okay, a crest is at its highest point. So that's our crest. And the trough at its lowest point, here's an example of one. Trough. Sorry for the handwriting. Okay. Hey, how many wavelengths are represented in the wave above? If I start here through one cycle, at this point I've got one wavelength. Go through all the way again. I have 2 complete wavelengths. So how many wavelengths? I've got 2. And what is the amplitude of the wave? I go from that center point 0 up to its maximum displacement away from 0, 5. So I see it's 5, and then the units here, centimeters. Okay. Next, let's take a look at problem 2. It seemed like several people had questions about that. Hey, so use the grids below to draw the following waves. This is going to look like our harmonic motion graphs, but instead of the horizontal axis being time, it's going to be distance. Okay, be sure to label the y-axis to indicate the measurement scale. So we have a wave with an amplitude of 1 centimeter and a wavelength of 2 centimeters. Hey, so I'm going to put 0 centimeters in the middle, and I'm going to use 1 centimeter per division here. That'll work out fine. Okay, this will be in centimeters, and then below -1, -2, -3. Yeah, I'm going to put a scale. I'm going to use 1 box for each. Okay. Hey, I'm going to label the x-axis here. I'll start at 0 centimeters. I'll just make 1 per division. Kind of getting the idea here. Okay, so I see that I have an amplitude of 1 centimeter. So the easiest way I'm going to start is up here at 1 centimeter. Okay, and I have a wavelength of 2 centimeters. That means it's going to go all the way down and back up by the time we get to 2 centimeters, which means that the trough is going to be at 1 centimeter. So I'm going to go ahead and mark those every 2. This is going to be a little trickier than I thought. Every 2 centimeters I'm at a crest. Just going to put X's here. Sorry about that. Let me go erase that mark. Back to my pen. And then I'm going to mark a trough every 2 centimeters as well. Okay, but important thing to remember, I start up, down, and then back up in 2 centimeters. I don't go from the peak down to the base in 2 centimeters and then back up. That would be a period of 4 centimeters. Okay, hey, so I have my peaks or my crests every 2 centimeters because that's the wavelength here, and then I end up having troughs every 2 centimeters. I'll start up here and then just draw my smooth as best I can sine wave through these. Okay, and I've finished the sine wave all the way out to 18 centimeters. Leave the next part for you. You can probably figure out how to make that next wave amplitude 1.5 centimeters and a wavelength of 3 centimeters. Remember, that's the distance from, let's say, all the way up back down, and all the way up. That's going to be a distance of 3 centimeters. Okay, last one seemed to cause some problems with this number 9. Okay, we have the period of a wave is equal to the time it takes for one wavelength to pass a fixed point. You stand on a pier watching water waves and see 10 wavelengths pass by in a time of 40 seconds. What is the period of the water waves? Remember, this is a little bit like our pendulum experiment. We take the amount of time. Okay, it took 40 seconds, and the period is the time for one complete cycle. And one cycle is the wavelength. The wavelength is the time or the distance from one crest to the next crest. So we'll end up dividing that by 10 wavelengths, or another way of saying 10 cycles. Oops, I think I misspelled that. So I take 40 seconds divided by 10 wavelengths, and I get 4 seconds per wavelength or per cycle. So that is our period is equal to t. What is the frequency of the water waves? Remember the inverse relationship. They're actually reciprocals. Frequency is equal to 1 over t. So in this case, 1 over 4 seconds is going to equal 0.25, and the unit for frequency is the inverse of second. It is a hertz. Last one, if the wavelength is 3 meters, what is the wave speed? Hey, how are those values related? Remember, our velocity is equal to the frequency times the wavelength. Let's go ahead and put in some numbers. Our frequency, 0.25 hertz, that's the same as a per second, and our wavelength we found was, let's see, 3 meters. 3 meters, so we have 0.75 meters per second is the speed of our wave.